All right, I think, well, now it went back from my current slide again, so let's try that again. There we go. Okay, now, still think we're sitting at 10 people, right? Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 people. So hopefully more will be coming in. But let's do a quick review, which really, Valerie or somebody's question was really good on it. What are we doing today? Okay. We're going to start in chapter 17, and we probably won't finish it. We probably won't even come close to finishing 17 today. Maybe get close to halfway through it. But we're only going to go from now until 4:15. Because at 4:15 we're stopping. I know lab technically doesn't start until 4:45, but today we're stopping at 4:15 because we want to go over the chapter 16 lab. And there's some things we'll do in class. There's other assignments you'll have at home. So that's what we're going to do. So stop me not today at 4:45. Stop me today at 4:15 if I start going too much into chapter 17 past 4:15. Stop me right there. Now, I sent out the chapter 17 lab last week also, so I hope all of you have that. If you don't have it, be prepared to get it by 4:15 so you can see what we're talking about, and however you want to write the answers down. If you've got it printed out for you, do that. If you want to write them down as we go, do that. This is going to be a different kind of lab. In fact, a lot of the labs you're going to notice way different from one another. I mean, they're going to be kind of all over the place. And that's sort of what makes this course fun, but it also makes it sort of challenging. This is the first time I've taught this class virtually, because the last time I taught the class was on the first mini term of spring, and that was over with before we went off campus. So I'm still adjusting this class to a virtual environment. So the lab we're doing on chapter 16 today is basically the lab we would have done in class, no change. Just like the chapter 15 lab, we did that one. That was just about exactly like we would have. Whereas the chapter 14 lab, I couldn't do that one. There's just no way to do that lab, or a very hard way. So I had to make up a brand new lab. So the one we're doing today is going to be very similar to the one we did in class, and I hope we can walk our way through it and talk our way through it. It would be better if we could see you in person, but I think it's one that does allow for that. Now, the chapter 17 lab is going to be sort of fun too. It's going to be a completely different kind of lab altogether. Okay, so we'll get there when we get there. All right. Any other questions? So we'll go and do start in chapter 17, go to 4:15, stop there, and do the lab for chapter 16. And part of that lab, as I said, is going to be a homework assignment that's going to take you probably more than 2 weeks to do. Okay? That sounds terrible. It's not that bad. We'll see when you get there. Okay? But then the bigger part of the lab we're going to do together as a group, just like we did the last lab as a group. Okay. Then next time we'll finish up 17 and hopefully do that lab on Wednesday. But we'll see. Any questions before we get started? Was that fuzzy enough to throw everybody into total confusion? Okay. Let me make sure nobody else has tried to join.
Did you ever get all the first test in?
Did I get all the first test? Is that what the question was?
Yes, sir.
Okay. The answer is I don't know. And no, this was before you came in. I was explaining this. I was out of town all weekend, and we were way out in the country. We're over in Georgia. Terrible internet, and then too, it was a beautiful weekend. We had a lot of work to do on the farm, and I worked the entire weekend. I thought maybe we'd have a rain break and I'd be able to check some internet, as it turned out, well, we didn't have a printer over there anyway, so I couldn't have printed off the test. So no, I don't know if everybody's turned in the test or not, because I haven't been able to get on the internet since last Thursday afternoon about 5 o'clock, because I had a class that started, oh, actually before that. No, yeah. I had 2 advising sessions on Thursday. Then I had about an hour of time that was going to try to print off things. I had emails that I had to deal with. The dean and some others had things. I only got to print off 4 tests, or 4, yeah, I think they were all 4 tests. And, but not all from this class, 2 from this class and 2 from another class. And then from then on, I was either on the road, on the farm, on the road, or in class ever since. So I haven't been able to get back home, and I'm going to try to print off as many as I can tonight. I'm probably going to run out of juice pretty quickly, but I'm going to try to do what I can tonight. And then tomorrow morning I've got class at 8:30, another class at 11, and after that I have advising on schedule, but I haven't seen my email, so I don't know if I have any advising appointments yet either. If I don't, I'll get more things done for y'all. If I do, I'll be advising and then get things done for y'all. So that was a terrible long answer to say no. I don't even know if everybody's turned in their test or not. Those that have, 2 of them I haven't graded yet, and I haven't been able to check emails to see if everyone turned them in. So as soon as I have a chance, I'm going to try to get caught up on emails. And once I get that done, then I'll try to get the grading done. And once that's done, probably I'll be able to answer your questions. So sorry about that. Any others? Maybe I can answer a little more positively. No, sorry. Is that okay, Roy? I know that was a terrible answer, but.
Oh, no, you're fine.
Okay. Any other questions before we get going today? Okay. Well, just to give you an idea of where we are. And I believe, now that I think about it, did we do this slide?
No.
Okay, we didn't do anything. Okay. All right. We've just finished the astronomy part of the course. Okay. If you recall, this course is basically 4 pieces: astronomy, earth sciences, meteorology, which we actually call weather and climate, and then oceanography, which we call Earth's waters. That's the title of the chapter. Okay? Now, the first part was astronomy. We're through with that. Once you do the lab that I'll be giving you today, well, I've already given it to you, but we'll be going over it today. And after y'all turn in that first, second, and third test, we'll be through with astronomy. Today we're starting the part, and your text calls it earth science. I believe the course description called it maybe geology, but maybe it was earth science there too. I don't know. But earth science is going to cover this chapter, rocks and minerals. Then we're going to cover plate tectonics. Whoops, here comes Nakia. Let me get her in. But I think she was in already, wasn't she? Yeah, she'd been here before. She's just coming back. So evidently she got booted out or bad connection. Let me make sure we still have the right number of people. Yeah. Oh, actually, we lost somebody else. Okay, so hopefully they'll be back too. Maybe that's Nakia. All right, so we're starting earth sciences, which will be geology, this chapter, basically rocks and minerals. Then plate tectonics, next chapter. Then building the Earth's surface, next chapter. And shaping the Earth's surface is the 4th chapter. Okay? That's the biggest group. Okay? Then after that, we've got 1 chapter on weather and climate. That's the meteorology chapter. And then we have 1 chapter on Earth's waters. That's the oceanography chapter. Okay? So that's how we're doing. So we're not quite halfway through. We're starting the second big group. The last 2 groups are really small, but this is rocks and minerals. Now, this picture you see here is a picture of, I think these are called rhodochrosite crystals. Now, you don't have to know that, but they are beautiful, aren't they? Now, can't tell how much they're magnified, but when I look at the one in the book and the one here, these may not be the color's right, but the crystal structure looks a little different. So maybe they're a different crystal. But anyway, Rocks and Minerals is the title of the chapter. We're going to do it in the reverse order. We're going to talk about minerals first and then rocks, okay? But it just sounds better, rocks and minerals, I guess. So anyway, well, now I can't advance the slide until I click on it. Okay. So what's the core concept here? Earth is a dynamic body that cycles rocks and minerals through ongoing changes. Now, actually, if you think about the first three chapters, the astronomy chapters, if you think about it in a sense, we talked about how a star was formed from a cloud of gases, that somehow some perturbation made them come together and became a protostar and then a star, and then they lived a life of millions of billions of trillions of years, and then they started wiping out, and at the end they blew up and blew gases back into the universe. Okay? Later, here's David coming back. So he must have got kicked out too, because I had him here before as well. Okay? So in a sense, the whole universe is going through cycles of formation, unformation, regrouping, ungrouping. The reason we have the periodic table, which would have been covered in Physical Science 2, chemistry part, which is before this in the book, is we've had enough of these cycles of stars exploding and stuff. You have this vast variety of elements and compounds and things like this. So, same thing here on Earth. Dynamic body cycles rocks and minerals through ongoing changes. This one that you see here on the slide, we'll see this later in the chapter, in fact in the second half of the chapter when we're talking about rocks. This is one called, if I can remember the name, it starts with G, and I cannot remember how to pronounce this. Not an easy name at all. I'll get it in just a second. Well, I thought I would. It is a metamorphic rock. Here it is. Gneiss. Okay. The G is silent, but it's gneiss. It's a piece of gneiss. I don't know if you can read that here. I can't, but maybe you can. What it is, this was, at one time, the various pieces of this were all igneous rock. We haven't even gotten there yet. Then they became sedimentary rock when everything was in flat layers. And then the layers got distorted through things we'll be talking about in this chapter. And that's why on this figure here you see all these weird looking shapes. And this rock is, I think, one of the oldest rocks that has been discovered on the planet. Okay? It says it's a banded metamorphic rock, very old, at an age of about 3.8 billion years. Probably among the oldest rocks on the surface of the earth. Okay? This rock has gone through so many stages. Okay? And probably fewer than others have, because this is still the same rock it was 3.8 billion years ago, which has been a long time. Before that, it was going through stages. So it's a dynamic process. And just about after every chapter, you're going to learn something called the cycle. We're going to talk about the rock cycle. We're going to talk about the hydraulic cycle. We're going to talk about cycle after cycle, which means things change going back to what they were before, remaining the same. That's what we're talking about here. Earth is a dynamic body that cycles rocks and minerals through ongoing changes. Okay, and again, I have to click on the slide to get it to advance. Now, let's start with 17.1, solid earth materials. Now, some of this isn't going to be solid either. Why solid earth materials? Well, the last chapter we do is going to talk about the liquid on the earth, water, okay? So we're not going to cover that here. The gas around the earth is the atmosphere, okay, mostly, okay? That's going to be talked about in a chapter we really don't do too much, but we'll talk about it when we're doing the weather chapter. So we're not going to do that part. We're going to talk about the solid earth materials, okay? Now, I look out my window right here and I see our backyard, okay? And in our backyard, there are some rocks. I can see a couple of them if I look real carefully. There's soil. There's other solid earth materials there. Now, there's man-made materials, but there's solid earth materials. We're going to focus on the solid earth materials, okay? Now, how would you describe them? Non-uniform distribution of matter. What do we mean by that? Well, if I go out in my backyard and start digging, I'm going to hit a variety of soil types. Mostly a pretty heavy clay. I've dug it. I know that. Mixed in with that is a lot of organic matter. Leaf mulch, bark mulch, pine mulch, various things. We've added some of that, but others has been natural falling from the trees and things like this, and sticks and stones and stuff. Okay? So there's a variety there. But if I dig, and when I dug my patio, I ran into a whole bunch of rocks. Big old heavy rocks, okay? Little rocks, big rocks, all sorts. So this is a non-uniform distribution of matter, okay? Now let's get way beyond what we could dig with our hands, or with shovels, or with equipment, or with the biggest drills that we've got going. What if we get down into the earth? Well, there we're going to find no longer solid earth materials. We're going to find materials that are so hot the rock is melted. Okay? Now, why would the rock melt? Well, I may have had you do this before, but if not, I'll have you do it now. Take your hands and put them together. I'm not going to have you pray or anything, or maybe you're already praying, I don't know. But rub them together. But press on them while you're rubbing. And what do you notice? They get hot. Why do they get hot? Two reasons. Pressure and friction. Okay? Well, guess what? As you go down into the earth, there's more and more and more weight above you. That's pressure. And that's forcing the molecules closer and closer together. And it's always moving. Here's David again. He must be having trouble staying in class, okay? Hopefully he'll get back in, okay? And what happens, it gets hot. Remember, just like the core of the stars. They started as a mass of gases, and as they accumulated more and more and more, they got hotter and hotter and hotter, and finally got to ignition of, it's not really ignition, but they call it that, of fusion, okay? We don't get that hot. We don't get anywhere close to that hot, but it's hot enough to melt metal, okay? So we have a molten core that contains most of the heavy elements. The two major ones, and the one major one is iron, but then number two down there in the core is nickel, okay? Now we have iron that reaches the surface, and some nickel that does too, but iron is predominant. And there's a reason for that. Remember the process of the bigger stars, more massive stars. They started off, well, all the stars start off hydrogen to helium fusion, and then once the hydrogen's used up, if they collapse again, then it goes helium to carbon, and at that point the smaller stars and the medium stars stop. They don't have enough fuel, don't get hot enough to do any more fusion beyond carbon. But the heavier stars keep that fusion process going, and it goes carbon ultimately up to iron. And iron is the last product of that spontaneous fusion as it gets hot enough. After that, it doesn't. But the heavier metals you see on the periodic table, they happen when those massive, massive stars then blow up and then collapse again. That is not a natural fusion process. That's where the heavier metals come from. Okay? Everything beyond iron in the table. Nickel is right next to iron in the periodic table, so it's formed about the same time. So, non-uniform distribution of matter. On the surface, we got a whole bunch of stuff. We got soils, we got rocks, we got elements, we got various things. Even under the water of the oceans, you got materials there. But under that, way under that, you got a molten core. Now, where we live is this thin surface crust. Okay? And in this surface crust, you have mostly lighter elements. Things on the upper side of iron in the periodic table. So you have the lighter things like carbon and calcium, magnesium, nitrogen, oxygen. You have all these things. And in this thin surface crust, there's only 8 elements, mostly lighter elements, that make up almost 99% of that crust. Okay? Now we're talking about the solid earth materials. You're going to be surprised at what some of these elements are. They're the lighter elements. Okay? Now, before we get to that though, rocks and minerals make up the solid crust materials. Rocks are combinations of minerals. Minerals we're going to get to in just a few minutes. Okay? Here are those 8. Well, again, I have to click the slide to get it to advance. Okay, here they are. Now we're going to start with the Earth's crust. And you might say, this slide is wrong. We're talking about solid Earth materials. And what is the number one element in those solid Earth materials? Oxygen. Almost half. Wait a minute. Time out. Isn't oxygen a gas? When oxygen is alone oxygen, yes it is. It's normally normal temperatures and pressure. Elemental oxygen is a gas. This oxygen is not an elemental form. This is oxygen that's combined with other things. Well, what other things might you ask? Well, do you have any oxygen in your body? The answer is yes. Part of it is the air you breathe, and it's in your lungs, but it ultimately goes to your blood. But when it's in the blood, you might say it's a gas, but really it isn't. It becomes captured by the hemoglobin and becomes an iron oxide, Fe2O3. Now, when it gets to your cells in the blood, then the cells rip off some of the oxygen, and then the oxygen that's left is FeO, ferrous oxide. The other is ferric oxide. This is ferrous oxide. So that oxygen in your blood was actually part of a solid molecule for maybe a few minutes, maybe a few hours, but whatever, it was part of a solid. Then it became, they ripped it off, and that your body made oxidize, say, carbohydrates with it, and then you breathe it out as carbon dioxide, which is another gas. You breathed it in as a gas, one gas. It came out as another gas, but it still was oxygen in there. And in between, it was all sorts of things, okay? Well, in the Earth's crust, and in all parts of the Earth, oxygen is all over the place in solid form. Not solid oxygen, but, and we'll learn this a little bit later. Let's go on to number 2. Number 2 is silicon. Now, silicon is obviously, I hope, obviously a solid, okay? A very lightweight solid, by the way. Most silicon is in the form of silicon dioxide. Well, I won't say that, but similar to it. Well, guess what? silicon dioxide. That's 1 silicon for 2 oxygens. Look at those ratios. They're almost 2 to 1. Not quite, but close. 2 oxygens for every silicon. A lot of the sand particles you see down on the beach, that white, pretty sand, if you looked at individual crystals of that sand, especially if you had a magnifying glass or a microscope and stuff, you'd see a beautiful crystal of quartz. Say again? What'd you say? All right, maybe you weren't talking to me. Okay. Well, that's a solid form. And yet there's more oxygen in that than there's silicon. Okay? Oxygen can be in a solid form when it's combined with something else that's a solid. Okay? Number 3 in the Earth's crust is aluminum. 8.1% of the Earth's crust is aluminum. Well, actually, let's go back. I said that it's in quartz form. That's only just a little bit. Most of the solid form of silicon and oxygen is in the form of silicates. SiO4. Okay, 4 oxygens for every silicon. Some is 2 to 1. That's, but silicon is heavier than oxygen, so it doesn't quite balance out the numbers wise, percentage wise, but that's what you have. The next most predominant form after silicates is aluminates. Aluminum is AlO3s. Those are aluminates, okay? And there again, you have so many aluminums, 1 aluminum for 3 oxygens, okay? So no wonder oxygen's all over the place. And then the iron. Now, some iron in the Earth's crust is pure iron, is just solid iron. But a lot of the iron in the Earth's crust is iron oxide. Like I said before, ferric oxide is Fe2O3, ferrous oxide is FeO. So a lot of that. When I mentioned clays before, what color came to mind when I said clays? Anybody?
Red.
Red clay. Guess what? Clay is not red. Clay is really a milky white, almost colorless.
Grayish.
And gray, there are gray clays too, and I'm so glad you said that. But really, that pure clay is not really all that gray. It's a very light gray, more of a milky kind of color. What is it that gives it that darker gray color or the red color? Iron oxide coatings on the clay particles. And the red clay is the iron oxide. The grayer clay, where do you see gray clay? You mentioned it. Where do you see it? In your yard or somewhere else?
I don't know. I see it in I just see it out in places, fishing, some places. I see it. Riverbeds. Different areas. I go kayaking, I see it.
Oh, okay. Bingo, you just hit it. Where there's water, where you have a large quantity of water, the iron gets reduced. Like I said, there's ferric oxide, which is bright red, and there's ferrous oxide, which is gray. Okay? That's ferrous oxide. And guess what? You got that in your body too. What color is blood? Anybody? You might think it's a trick question. It's mostly red, right? But it's red when there's oxygen in it, when it's ferric oxide, when it's carrying that red. Because what your hemoglobin is, that's what carries the oxygen to the various parts of the body. It's a claw. And in the center of that claw, there is an iron atom. Actually, an iron ion. And when the iron is connected to 2 irons connected to 3 oxygens, that's the ferric or red iron. And when it's only got 1 to 1, 1 oxygen for every 1 iron, it's a gray, ferrous oxide. And what happens in your body, the arterial blood is red. You don't see it on your surface because arteries are deep, okay? You don't want to cut an artery, okay? That's being pumped out. That's carrying the oxygen to the body so you can move your fingers and talk and listen and do all these things. That's how the oxygen's getting there. But when the cells take it from the iron, the hemoglobin, take one of the oxygens away, then it becomes ferrous oxide. That's your venal blood. And what's that? It's blue, gray. That's why your veins are blue, your arteries are red, because your arteries are carrying the oxygen to the blood, to the cells in your body, and when they come back, they're gray. Just like that waterlogged, when you're being kayaking, you see that gray clay. That's because the ferric oxide has changed to ferrous oxide. It's lost some oxygen. On the hill.
Oh.
Yes.
No, I was just.
Oh, yeah.
Saying.
Okay. The house where I grew up most of my life in Burke County, Georgia, where I was this weekend, I didn't go to the house. My sister lives there. She came to see us. So I didn't get over to the house, but there was a hill on the field right next to that. Red clay hill. I mean, just solid red. But down at the bottom, there's a low area, and they sometimes call it a Grady pond. It's swampy during the wet season, dries out in the dry season. But down at the bottom there, it was gray. And the soil, just like you described, red on the hillside, gray at the bottom. And I always thought it was because the sand from the hill had washed into the low area, and it was sandy down there. Until I tried to cultivate it, and I saw, nope, that's as heavy a clay as there is up there. What's the difference? On the well-drained part, well-oxidized red clays, when it got to the bottom, it got reduced. The iron got reduced to ferrous oxide, and it became the gray color. So that's exactly, you're right on the money. When you said kayaking, I knew right where you saw it. It was on the river banks or creek banks or whatever, and that's that clay.
Vein.
Say again?
Like in a vein.
Yeah, exactly. And yeah. So that's it. So iron, that's number 4. Calcium, most of the time it's not just pure calcium out there. It's calcium carbonate, calcium oxide, calcium somehow combined. When you hear carbonate, carbon with 3 oxygens. The ATE means there's oxygen involved. So calcium carbonate would have 1 calcium, 1 carbon, and 3 oxygens. That's where all the oxygen is. It's tied up in other compounds. Sodium. Sodium is usually tied up with some of the silicates. And we'll talk about these later too. So I won't go into great detail. Potassium, that's sort of trapped in between the silicate layers and the aluminate layers. That's where your potassium sits. So it's surrounded by oxygen. Magnesium, it's a lot like calcium. Magnesium sulfate, magnesium carbonate, magnesium oxide it could be. Sulfate, 1 sulfur, 3 oxygens. Carbonate, 1 carbon, 3 oxygens. Oxygens all over the place, but it's combined with all the rest of them. And then everything else is your 1.4%. That makes up the difference between 98.6% and all the other elements in the surface of the earth put together, 1.4%. Okay? So that's the surface. Now, if you talk about the whole earth, which includes that molten core, everything else besides the crust, iron becomes number 1. Why? Because the core is mostly iron, where it was just a tiny part of the crust, like 5%, when you count the whole core, and that we'll talk about later, the mantle, that's mostly iron. Then it cuts up to be 1/3 of the solid material in the earth is iron, which is the final product of your fusion reactions that happen in the huge stars. No wonder it's mostly iron. But number 2 is oxygen. Not oxygen that we're breathing. That's in the atmosphere. That's a small amount. What we're talking about there is oxygen combined with all these other elements. Okay? Silicon drops from 27 to 90 to 15, 16, 28 to 16. Magnesium increases from 2.1 to 13.9. And actually, you'll hear a lot of the minerals called ferromagnesium minerals, because the magnesium really combines with the iron a lot. But again, those are deep, not so much on the surface, so there's some here, but not much. Okay? Then comes your nickel. Remember I said iron and nickel are mostly in the molten core. Nickel's mostly down there in the core. Not much. You didn't see that. That was part of the others here. So it wasn't even included on the surface, though there is some on the surface. That's where they get the nickel mining. But Earth's crust, I don't say surface, but Earth's crust. Okay? And then calcium has dropped from 3.6% to 1.8. Aluminum has dropped from 8.1 to 1.5. Sodium was 2.8 down to 0.2. And then all the others, that would include potassium, you don't see here. That would be included in the others here. Magnesium, you don't see here. You do up here. That would be included in the others here. So everything else, all the other, and think about precious metals like gold, silver, copper. You don't see them in any of these. They're always in the other. That's what makes them precious. They're very rare. There is mining done and stuff like that, but it's just fairly rare. Okay. So, rocks and minerals make up solid crust materials. Now, that was 17.1. We're moving now to 17.2. Like I say, the title of the chapter is Rocks and Minerals, but we're going to do minerals and then rocks. The chapter does it that way. We didn't just choose to do it. The chapter does. So let's first talk about what in the world is a mineral. Here is your earth science definition. Naturally occurring, inorganic, solid element or compound with a crystalline structure. 4 key ingredients of being a mineral. Naturally occurring, inorganic, solid element or compound with a crystal structure. Okay. Now, what does that exclude? It cannot be synthetic. Nothing made by man. So like I said, I look out at my backyard. I see an aluminum dog kennel that the dog has hardly ever been in. Okay. That aluminum was a solid earth material at one time, but it's been processed, refined, shaped until it's no longer what you classify a mineral. It is synthetically, man has fiddled with it and made it not a different material, but changed its form enough. It's no longer a mineral. When it was located down in the Earth's crust, in the Earth's solid Earth, we saw aluminum was there in both places. Yep, it was a mineral there, not after it's been treated like it's been treated here. Okay, so that's one thing. Can't be synthetic. Number 2, not produced by a living organism. Now, what we mean by that, I look out at the backyard and I see a lot of trees. They have solid materials, right? The wood is solid. Yeah, but that's living organism. That's not mineral. Where did they get the material in that wood? Well, the calcium came from the ground. And by the way, cellulose is a complex carbohydrate, and calcium forms sort of the structure of those cell walls, if you've ever done any biology. Okay, so the calcium came from minerals, but not after it became wood. Then it ceased being a mineral. Okay, now it says solid element or compound. If I look out there carefully, I don't know if I can see it from here, I see, oh yeah, there's our dog tub, okay? In that is some water. She likes to sit in her tub, okay? We don't have it full of water because it got pretty dirty and we dumped it, and it hasn't filled again, or we haven't filled it again. So water would not be included, okay? That is not a solid element. The air is not a solid element, okay? That's not a crystal structure, okay? Now, or it's not a solid structure, okay? And then the fourth thing, it must have a regular repeating pattern, okay? Now, here's an example. I'm going to get a little bit of chemistry in on this too, because technically they're assuming you had the first half of the book. We haven't, but I'll sneak some in on you. A mineral that's out there in nature is called halite. Whoops, here comes Capri. Good. Okay, she hasn't been here before today. Okay, here's Capri. Don't know if she's here yet, but she's coming in. Okay. Now, Capri, if you're here now, we're in chapter 17, which is Rocks and Minerals is the name of the chapter. 17.2 is the minerals part. The next part will be the rocks part. So the title is backwards. We're talking about minerals. What are minerals? We're just talking that they have to be in a regular repeating pattern. And the example here is halite. Now, halite is a mineral made up of a solid compound called sodium chloride. Now, that doesn't look like that'd be a sodium, but the symbol for sodium, I think in Latin it was natrium, and that's where the Na comes from. Chloride, Cl, that sounds about right. It probably has an H in it, you know, when you spell it, but Cl is what we use for chloride. Maybe not. It doesn't have one. Sorry about that. Okay, sodium chloride. What is sodium? Sodium, and that was one of the elements in the Earth's crust anyway, was sodium. Now, sodium very seldom exists as an element. Sodium is a very, very highly reactive element, so it always combines with something else. When they extract and pull apart sodium and make it pure sodium, if you've ever seen any, it's been in a bottle in a chemistry lab, and it would be a solid, sort of a yellowish kind of a solid. They call it a metal, but it's not a very strong metal, not a heavy metal at all, a metal, but it's so reactive that they have to keep it under oil. It would be in the bottom of a bottle that contained oil. It would be a solid down there. If you ever exposed it to water, it would explode. I mean, literally explode. Water, which usually you use to put out fires, it would cause sodium to explode. Give off enormous amounts of heat because it's that highly reactive. Okay, so there we have a yellowish solid metal that's explosive when it touches water. Chlorine, what is chlorine? Chlorine is a green gas, okay? It's a poisonous gas that you would definitely not want to be around. Some of the rail cars you'll see going in the thing, when you see those big tanker cars on the trains, sometimes you'll see chlorine, warning, chlorine. If that car ever overturned and that gas started leaking out, they evacuate the entire area. It's a poisonous, green, obnoxious gas. So here we have a yellowish, explosive metal combining with a green, noxious gas, poisonous gas. Does anyone know what sodium chloride is? Do any of you happen to have on your desk right now, you're not going to lose any points if you answer this correctly, say some potato chips or pretzels or anything like that? In your house, we got some pretzel chip, Actually, goldfish pretzels downstairs. What's that little white stuff on them? You know.
Salt?
Salt! Table salt. That's sodium chloride. It's made out of a metal that's explosive and a green gas that is poisonous, but when they combine chemically, they don't look like sodium, they don't look like chlorine. That is sodium chloride. It's made up of 1-to-1 sodium chloride atoms, actually ions, that make up sodium chloride compound. That is, you're absolutely right, it's salt. Table salt is refined halite. The halite probably has a little bit of contamination in it. Yeah, that's expected. It's in nature. They melt it or they dissolve it, get the contaminants out of there, and then resolidify it and form table salt. So therefore, it would not be a mineral per se because it's been refined. It's somewhat synthetic. But the halite that it came from, and I'm guessing this, any of you ever make ice cream in the summertime? Have an ice cream maker? Or have you seen your grandparents do that? Homemade ice cream? Or have you heard people talk about it?
My mother and I used to make homemade ice cream.
Okay. And
my granddaddy.
Okay, I thought it was a few generations ago. How did they get that to freeze? If they just put ice around the outside, it would never freeze. What did they put on the ice?
Salt.
Yes. And they called it rock salt, didn't they? Or did they? That's what my dad used.
It used to make me get on that thing, and it would take me 30 minutes on that thing, and it would wear me out.
Yeah, it certainly would. I've done it too. Turn that crank and turn that crank. My wife won't have those. She has them electric now. But when I was a boy child, yeah, I had to turn that crank. But if you didn't put salt on the ice, it wouldn't get cold enough to to freeze the ice cream. So you had to keep it. And we used rock salt because that was cheaper. My dad was really cheap, okay? And that rock salt, I bet you, was what they call halite. And you know, when it was left over, it had some grit in it and stuff like that. A little bit of quartz, a little bit of other things in it, who knows what. But the actual salt part of it was halite, okay? Now here's how, yuck, I have to go back and hit my screen again. Okay. Here is how that salt crystal is put together. Now there's an error on this slide, and I want you to see if you can find it, okay? But I don't know, what would you call that, taupe or something like that, ions here are sodium ions, and the blue ones are chloride ions. And every sodium is connected only to chlorides. Every chloride is only connected to sodiums, okay? And they form little cubes, and we call this a cubic structure. It's a repeating pattern. Every sodium is connected to chlorine, but chlorines are only connected to sodiums. Does anyone see the error here? This one right down here. They show that as a chloride. That's not a chloride ion. That's a sodium ion because it's connected to other chloride ions. It can't be. That has to be a sodium. So they got the coloring wrong here. They blew that one. In your book, they got it right. If you have a book, you see they corrected this in the subsequent editions. But in this figure, they got it wrong. Okay? It's a repeating pattern over and over again. So sometime, if you have a pretty strong magnifying glass, like maybe Granddad has one to read the paper with, go out and rip off his magnifying glass for a minute, take it in and look at some table salt. Under the really strong magnifying glass, you'll see they're little cubes. You can see those little cubes there in the figure. They show on figure 17.4 on page 439 in the book, that may be your 17-4, they show a magnified picture of salt crystals at the top of a salt shaker, and sure enough, you can almost see the cubic pattern there. Okay? So that's one example of a mineral. That's what we're talking about. Naturally occurring, inorganic, meaning not coming directly from plants. Now you might say, and later we'll talk about this, some minerals maybe a few thousand years ago came from plant materials, but they've been changed back to being naturally occurring, okay, inorganic, and must have that crystalline structure, and they must be solids. Okay, so let's look at the crystal structures. Now I can just about hear you now when I start naming these structures. You're going to freak out. Don't think you have to know them. Most of this is so you'll at least be exposed to them at least once, so that if you ever see them or recognize them again, you'll say, oh yeah, I remember that. Okay. Now, crystal structures can be made up of only one kind of element. We're going to talk about diamond, girl's best friend, right? Diamonds are made out of pure carbon. Now, if they have any color in them, that means they have some slight impurities there. But if it's a sparkling, clear, really strongly reflecting diamond, that's almost pure carbon, guaranteed. Okay? And we talked about this with the white dwarfs. Remember? Lucy in the Sky with Diamonds. Compressed carbon, that makes high pressure, high temperature carbon, that becomes diamond. Now, actually, there was, I don't know, he probably still is, over at UAB, one of the physics professors, his research was on synthetic diamonds. He took carbon and under huge amounts of pressure and high temperatures, he made diamond. Little bitty diamonds, gritty little diamonds, but they make great. Have any of you ever seen a diamond saw, they call it? It's not really made out of diamond. They encrust diamonds on the blade. It'll cut through anything, because diamond is just about the hardest naturally occurring material on the planet. Diamond. In our backyard here, some previous owner poured a concrete slab from one end of the backyard to the other, well, to where it falls off. I'm guessing about 75 feet long and probably 20 feet wide. Concrete slab. And it encircled some of the trees, a walnut tree, a pecan tree, and some trash trees like hackberry or something. We thought, why? We asked the realtor. He said, nobody seems to know for sure. One of the neighbors said they thought they'd put it there so the kids' clothes wouldn't get dirty when they were swinging on the swing set. I thought, yeah, a lot better for them to fall down on concrete and break an arm rather than getting the shirt dirty, you know, if they fell on the soil. I don't know if that's the reason, but anyway, they had reinforced concrete there. I mean, they had steel in it. And when we had it cut, so we wanted that thing out of there, they came in with a diamond-bladed, diamond-crusted blade and cut through that reinforced concrete. No other blade would do that. Diamond would. So it's hard material. That crystal structure is a three-dimensional crystal. Hard. Those chemical bonds are incredibly strong. They had to be. They're formed under such heat and pressure, they form really strong bonds. Okay. However, there's another kind of carbon-only compound. Has anyone ever heard of graphite? Anybody? What's in the pencil lead? That's graphite. Graphite is also found in other places. What were you going to say, Roy?
I just said yes, I know what graphite is.
Okay, and where do you see graphite? Were you going to say pencil leads? Or something else?
They sell it in like a powder form, and you can take it and like if you got a squeaky door hinge or something that's metal that's squeaking, you can kind of spray graphite or powder it, and it works kind of like WD-40, but it's not
okay.
wet.
You're absolutely right. It's a lubricant, which makes things, removes friction. So here you have one form of carbon compound, carbon only, diamond, which is the strongest abrasive you have that you use to cut through metal, and you have another compound of carbon only, graphite, which you use to lubricate materials to get through the squeaky hinge, you know. Well, why is that? It's a two-dimensional structure, not three-dimensional, and those bonds are very weak and they slide past each other and make it into a lubricant. Can you get any more different than? And graphite, graphite, the graphite lubricant you've used, isn't it sort of blackish in color?
Kind of gray.
Yeah, grayish, yeah. Whereas
Gray,
diamond...
shiny gray, too.
Say again?
Shiny gray.
Yeah, shiny gray. Whereas diamond is crystal clear. I mean, crystal, okay? It is clear as...
Like a little bitty tube.
Say again?
It's just in a little bitty tube.
I can't hear. Say again?
It's in a little tube.
Oh, yeah. Oh, the graphite? Yeah. And so how can you be more different from being an abrasive to a lubricant? And yet they're both made out of pure carbon. Now, another abrasive is quartz. If you've ever got any quartz sand in your flip-flop when you're down on the beach, it is an abrasive. I mean, you'll rub a blister in no time, you know, because that is a very, and what do we call it? Sandpaper. If you're trying to refinish furniture or shine up a metal or something like that. Sandpaper. But that's silicon and oxygen in a form. Silicon, which is a very soft metal, you might say. Oxygen, which is a gas, and yet it forms a really strong quartz crystal. The sand, okay, is one example. Now, what are these crystal structures that are so different from one another? They're based on what they call their surface symmetries. Now, don't sweat these. You don't need to know them or the differences. But just to let you know, here are the 6 major systems: isometric, hexagonal, tetragonal, orthorhombic, monoclinic, and triclinic. What names? You'll hardly ever see them anywhere else. Let's get a sort of a picture of what they are. Well, here is the isometric. Now remember our sodium chloride? Cubic structure. These are almost always in perfect cubes. Well, what makes a cube? All the sides are the same length. And all the angles are the same. In fact, to be a cube, those angles are all 90 degrees, right angles. Okay? That's your cubic structure. Now, why do they call it isometric? Metric means to measure, which means that either the angles or the lengths. And iso means the same. Isobars are regions of equal barometric pressure. Isoclines are equal elevations. Isotherms are equal temperature. You can see these things all over in physics, chemistry, and stuff. Iso means same. Metric means to measure. And a cube has same length on every side and same angle. Another form of an isometric structure is an octahedron. Now, octo means 8, and hedron basically means sides. This has 8 sides. There's a side, there's one, there's one, there's one. There's 4 on the bottom and 4 on the top. All of those lengths are the same, and basically all the angles are the same. Each of these are what they call equilateral triangles, and so all the angles here, if I can get my cursor to come back, there you are 60 degrees. Okay, every one of those angles is 60 degrees. Okay, and 8 sides all equal in measure. That's the octahedron. A tetrahedron, okay, is a 4-sided figure. Again, you have 4, and generally I think they are equilateral triangles. Here's one on the base, one on the back side, one on the downside, and one on the upper side. 4 triangles, and that's a tetragonal structure. 4 sides, but all the sides are equal. Okay? Now, remember when I said the aluminum silicates? Those are basically little octahedrons, and the aluminates are octahedrons. The tetrahedral structures are the silicates, and they form layers that make your clays. We were talking about before, the pure clay without the color made by the iron oxide are all combinations of silicate layers and aluminate layers. And they fit together fairly nicely. I don't know if the fact that this is 4 sides, that 8 sides, they're put multiples of each other. They don't look like they do, but they do. And in fact, sometimes they trap in between them potassium. And those are called a certain type of mineral that have high potassium content. That's beyond this. You don't need to know it. The dodecahedron. Deca means 10, and basically is like duo, 2. So this would be a 12-sided figure. And it's hard to count these and to keep up with them, but let's do the dotted ones underneath. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, there's 12 sides to that dodecahedron, okay? And all the lengths of every one of those sides are the same. Now, I don't see how the angles could be the same, because this angle right here almost definitely looks like it's a smaller angle than these other angles here. So I'm not sure the angles are the same, but the sides are. So those are your isometric equal measures, okay? Then you have the hexagonal structure. Hex means 6, and gonal means 6 sides again. Not hedron, but gonal, they sort of mean the same. Here's a prism, okay? 1, 2, 3, 4, 5, 6 sides, okay? That's a hexagonal structure, okay? Now here is a rhombohedron, which looks kind of a little bit like a cube, only here's a difference. A rhombus is a square that the elephant sat on, and it twisted like this. So the sides are equal, but the angles aren't equal, okay? Because it's been sheared a little bit. So this is a rhombohedron. It still has, but if you look at it, there's a top and bottom. That's 1, 2, and then 4 sides, 3, 4, 5, 6, 6-sided figure. But the angles nor the lengths have to be the same. These look to be shorter lengths than those are. So that's hexagonal, okay, meaning 6 sides. Here is a tetragonal, which again is 4-sided, but this is now gonal rather than a hedron. This is a 4-sided single figure. This is 4 different faces to it. 1, 2, 3, 4. Even at the top and bottom, 1, 2, 3, 4. These have rectangles here in the middle, triangles at top, but they're still 4-sided. Okay, tetrahedron. That is a prism. And frankly, that's what you'll see your quartz crystal. We'll see pictures of these, and you'll see those tetragonal structures in that, and they're absolutely gorgeous to look at. I'm trying to think what. Let's go back here. Remember that first one? In your book, that's why I said those look almost more cubic in structure. These look like they could be tetrahedron. I can't tell for sure because the definition isn't quite good enough to see, but they are definitely different crystals. Okay? Okay, so those are the tetragonal prisms. This is a prism. Anything that has a length, but then symmetry around it, around that length, that's what makes a prism. Here's an orthorhombic, okay? Now the rhombus that we saw up here, same rhombus here, these are not necessarily the same angles. Again, the drawing here makes it look a lot like a cube, only it's not. But this is orthorhombic, and I think the ortho means there's a lot more differences here. This side and this side may be the same, this side and that side the same, this side and that side the same, but none of them are the same as each other. So that's orthorhombic, and their angles are probably off too. Now, I can't figure out why they call this a monoclinic and that a triclinic. Mono usually means one, tri means three. I don't see any relation to those at all. But these are both prisms. They are in thing. So you don't need to know these. So don't sweat them. But just if you see a crystal and you recognize, hey, that looks sort of like a tetrahedron, that looks like a hexagonal shape, you'll see some of these things and you'll know, yeah, that's a crystal structure. The point here, they have these definite structures. They may be fairly complicated, but they all have definite structure. Okay? That's what we mean by crystal structure. Oh, here's some pictures. I knew this was somewhere. These are those salt crystals, halite crystals. Notice every one of them looks like a little cube. Maybe different size cubes. Some of them, the edges have worn off a little bit. Some of them are pretty sharp. Okay? Some of them may be fractured a little bit, but they all are a basic cubic structure. That's the structural unit for crystal of table salt. That's exactly what this is, as a isometric. I couldn't think of the name, and it's a cubic structure. This, on the other hand, are your quartz structure. These are quartz crystals. These are huge quartz crystals. I don't want that one in my shoe, okay? And I can't quite make out, but it looks like 1, 2, 3. It's either 4-sided or 6-sided. I can't make it out. If it's 4-sided, it's tetrahedral, tetragonal, okay? If it's 6-sided, it's a hexagonal, okay? I can't really tell. Maybe those are more hexagonal, okay? And here's another one. You see that pointed, where is it? Come on, there you are. There's a little point on it. Here's a point on this one. Different size crystal. This one's huge. This is much smaller. And you see the column or the prism type shape in it. Here's one going this way, some laying this way, and this one. And there's others that aren't as well defined. Okay? But that just shows there is well-defined order in these crystal structures. Okay? Now, turning from there, this book likes to do these little mistakes and misunderstanding. They talk about healing crystals, and maybe you know people, maybe you're one of the people who really believes in the crystals and wearing them will improve this, that, and the other, your health, depression, whatever. He says no scientific studies have found that these crystals are beneficial whatsoever. They may be very pretty and they may make you feel better, mostly because of their beauty. So that would be about it. That's his take anyway. Okay. Crystal structure was mentioned on page 439. Now we start a portion that sort of ties the first bit, the relative amounts that we have of these things, to these other structures. And we're going to now talk about silicates. Silicates are mineral forms that are made out of silicon, that's the silly part, okay? The ATE at the end, that's the oxygen part. And basically a silicate, as it says here, contains mostly silicon and oxygen, and it's usually 1 part silicon to either 2, 3, or 4 parts of oxygen. So oxygen dominates these silicates. However, they're called silicates. The cates, ATE, means oxygen is there. These silicates make up 92% of the Earth's crust. Now, let's think back on the crust. We haven't seen this yet. I think we'll see it in the second half of the chapter here. But the Earth's crust is a very, very thin skin, you might say, of the Earth. Now, when I say thin, several miles deep. Now, that sounds pretty thick to me, but when you consider how many miles the Earth is across, a few miles is nothing on the surface. Nothing. It's very, very thin. 92% of the Earth's crust is made up of silicates. The 8% is everything else. Now, what are these? These are the silicon oxygen tetrahedral units. Like I said before, and basically what you have is one silicon in the middle and 4 oxygen equally placed around it. Now, that doesn't make a square. That's not right. 3-dimensionally equally placed around it. That's a tetrahedral structure. Let's go back to that again. Notice here the silicon would be in the center down here, and there's an oxygen 1, 2, 3, 4. All equilateral triangles, all distances and everything the same. That's your basic silicate structure. Silicon in the center, oxygens on the vertices. Okay. Now, there are 4 different arrangements, major arrangements of these things. The isolated tetrahedron, which is 1 silicon and 4 oxygens around it. Those are the ones that are 4 times as much oxygen as there is silicon. These are isolated tetrahedrons. Now that almost sounds like that sand grain that gets in your shoe and irritates like crazy. Okay, very hard. That should be your sandpaper, type thing. But you also have chain silicates. So here's a silicate tetrahedron. It shares an oxygen with the next one, with the next one, with the next one. Here's sort of the figure of that. Here's the tetrahedral, like I said before. The silicon's in the center, right there, and the oxygens are on the vertices. Okay, and this is supposedly a 3-dimensional figure trying to draw on 2 dimensions. It's hard to see this exactly. Here is one triangle. If I can find my cursor, where does it go? There it goes. Here's one that's that line, this line, this line, and the dotted line across there. That's in the background. Here's this tetrahedron. There's the line, there's the line, there's the line. Here's the tetrahedron. I'm sorry. They're not connecting to the silicons. Well, they are. The bonding to the silicon, but I was trying to show you the faces. The faces leave out the silicon and go, goodness gracious, go from this silica oxygen to that one to that one. That would be a triangle. This one to that one to that one would be another triangle. The one that's on the back side would be this one to that one. It's that line right there, the dotted line to that one. Now that's what's distorting this picture, because that's in the background, but it looks like the biggest triangle. So that's what's going on. That's this triangle here is the base. Here's one side, another side, and the one coming toward us is this one. That's the line, and that's the other base. So the silicon's in the center of that. That's your isolated tetrahedron. Okay. And here's another picture of that. There's a silicon is a little blue dot in the middle, and the bigger red dot are your 4 oxygens that are around that singular silicon. And what they've done is sort of drawn that from the center of each oxygen, and there's one on top here. Here's an oxygen here, and inside of that is the silicon here. That forms that tetrahedron. There's a triangle side, there's a triangle side, there's a triangle side, and the whole base is the 4th side. Okay, individual tetrahedrons. Now, when they share one oxygen between 2, this oxygen right here that's underneath there is shared by this tetrahedron and that one. This one shares that one with this and that. This one shares this one with this one and that one. And this one shares that oxygen between this and that. That's now what they call a chain silicate. And the chain is not straight, it's wavy like this because the angles are not 180 degrees. They're at some angle of approximately, I'm going to say 120, but that's probably not quite true. And these form the chain silicons. Now we'll see in a later part of this chapter one of the chain silicates, and that's a fairly well-known material, asbestos. That is a sample of a chain silicate, and that's what people fear. Back when I was a very young boy, I remember advertisements on television bragging, and I can remember my uncle talking about it, bragging about the advantages of asbestos. It will not catch on fire. You can use it to insulate pipes and you'll never get hot and catch on fire. It may get very, very hot. It will not burn. Okay, it was a fantastic discovery, the use of asbestos, until they had used it for about a generation or two, and then they found out that people that worked with it got asbestosis, a really serious lung disease. That asbestos, when breathed in, the little fibers of asbestos, these little chain silicates right here, really do major damage to the lungs. And here's the sad part. There's only one kind of asbestos, or a few kinds that actually are damaging like that. There's several other kinds of asbestos that are really very beneficial, but most lay people don't know the difference, so therefore all asbestos is banned from everything, even though there are some non-carcinogenic, non-toxic, non-harmful asbestos materials, but no one will touch them. Okay, then you have your sheet silicates, and these form the sheets. Now each tetrahedron shares more than one or two oxygens with another. Oops, here comes Bridget. All right, good deal, Bridget's here. First time here today, so we get Bridget here. All right. Well, if I could get my pen to write, I'd mark her present. There, I got you. Okay, Bridget's here. Welcome. Okay, we're in Chapter 17, Rocks and Minerals, and we're in the part on minerals, 17.2, and we're talking about silicate minerals. 92% of the Earth's crust is made up of silicate, and we're talking the solid materials made up of silicate minerals. There can be isolated tetrahedrons with one silicon in the middle and four oxygens around it, or chain silicates, which each adjacent tetrahedron shares one oxygen with the other, so this would not be a 4-to-1 ratio. These they would share more than one, okay? And some of these are 2 or 3 are being shared. Those are sheet silicates. Now your sheet silicates are your clays, and most of the clays are a silicate here, and then an aluminate on top, and then another silicate, then a silicate, aluminate, silicate. Your clays are made out of these sheet silicates with some sheet aluminates too. Or framework silicates. And these would be not just 2-dimensional sheets, but 3-dimensional sheets. What's that? Okay. All right. So these are framework silicates that would be more than 2-dimensional. And that's why clays, by the way, are so slick. If you've ever driven on a clay road after it rained, you may wind up in the ditch, because those clays can be really slick when they're wet, because clays absorb moisture between the sheets and then they slide like graphite. Okay, they really are slick. Okay. Again, back when I was young and they were paving the road that we now have our house on, they were working it up, and when they're doing that, they bring in the clays and they use the clays that are there. And it was a rainy summer, and people would come down that thing where all of it had been, and they just slide into the ditch. My brothers just had the tractors ready to go out. I think I was in the Navy then, or college or somewhere, and they just they made a little extra money. They didn't charge people for pulling them out of the ditch. A lot of people offered to pay, and they would take it then, but they would do it for free just to be neighborly. But quite often they made a little bit of spending money that way. The sheet silicates were slick. The framework silicates would be a little less so. All right. Again, I'm going to have to touch the slide to move on. Now, your non-silicates, those would be the 8% of the Earth's crust. These are no silicon-oxygen tetrahedrons in any of the crystal structures. They all have to have crystal structures. They wouldn't be a mineral. But these are not made out of silicon-oxygen structures, which are silicates. 92% of the Earth's crust is silicates. Only 8% is made up of these others. There are then 8 groups of these non-silicates, and they're not evenly distributed. The most common of these are your carbonates. And again, the ATE means oxygens there. This is carbon, 1 carbon with 3 oxygens, carbonate. And these are the most abundant of the non-silicates. And we should know that living in Alabama here, especially in the area we do. A lot of our underlying rock formations, not so much silicates, but carbonates, limestone. Limestone is the parent material for many of our soils. And that's what makes some of those heavy clays, I think, that Roy was talking about. The fact that we're limestone-based rather than silicon-based. Okay? Though the limestones will have some. That's when we're getting into the rock part, which then mixes things. But the carbonates are non-silicates. Sulfates would then be 1 sulfur with 3 or 4 oxygens. Sulfates would have 4, I think it is. Sulfites would have 3. And you see those two sometimes. But in the non-silicate minerals, so sulfates, sulfur and oxygen. Oxides are just things with oxygen. That could be, in chemistry, you have the anions and the cations and the anions. The cations are the plus charges, the anions are the negative charges. Oxygen's always negative. So iron oxide, carbon dioxide, hydrogen oxide, anything that combines with oxygen. Now, some of those I named were metals, some of them are not. But the oxide metals are your non-silicate because there's no silicon involved with them. Sorry. Like I told you, I've had a long and tough weekend, and I've dried out. Everything is dried out. So periodically I'm going to have to get a sip or two of water because I'll just lose my voice otherwise. So, oxides are just some metal cation combined with oxygen, whatever it is. Sulfides are the same as that, so the IDE means there's only 2 things there, something else plus oxygen, something else plus sulfur. Hydrogen sulfide. I bet you've run into that before and you knew it if you did, but you may not have known it was hydrogen sulfide. If you have ever smelled rotten eggs, you have breathed in some hydrogen sulfide. That's the rotten egg smell. Because what is an egg yolk? It's yellow, almost, not pure, but high quantity of sulfur there. And when it starts mixing with hydrogen, that's when the egg is rotting. And that rotten egg smell is hydrogen sulfide. But there's many sulfides that make minerals too. One of them is called fool's gold. And I'm going blank on the name of it now. It's I believe a sodium sulfide, but the mineral name I've lost. We'll hit it later, okay? The halides, we saw halite is one of those. Now here's where that word comes from. They're assuming you've had chemistry. Of course, most of you have not. Maybe you had it in high school. But on the periodic table, and this is in your book somewhere if you got it, on your periodic table, the first column over here are your soft metals. There's that sodium we were talking about. Second column are called and these are called the alkali earth metals. I'm sorry, the alkali metals, and the alkaline earth metals. First column alkali, second column alkaline earth metals. Here are most of what we think of as metals. That's where your iron, nickel, and cobalt are right in there together. That's 26, 27, and 28. They're right there together, on like this. You come over here, and this is column 1, 2. Skip these. 3, 4, 5, 6, 7, and 8. It's how many electrons are in the outer shell, and the halides are the column 7. And that's your chlorines, your fluorines, your bromines, your iodides, those are your halides. So that's what they mean by the halide. Something combined with those area or column 7 materials. Halite is one because it's sodium chloride in that 7th column. Phosphates, a lot like your carbonates and sulfates, is phosphorus with oxygens. Okay, usually a phosphorus and 3 or 4 oxygens around. I think 4 is phosphate and 3 would be phosphites. Hydroxides are things combined with a OH anion. Okay, hydrogen. Hydroxide, sodium hydroxide, potassium hydroxide, aluminum hydroxide. There's a variety of those. That's an OH molecule or ion at the end. And then we have what they call the native elements, which are basically the things that don't combine much with other things like gold, silver, copper, sulfur, that are just almost pure elements. Okay, largely pure elements. All those don't have silicons in them. 92% of the Earth's surface are silicates. Only 8% are these non-silicates. And carbonates, the most abundant, are things like your limestones. But again, limestones are rocks, not minerals, and rocks have some other mixtures. We'll get to that later in the second part. Okay, so let's look at comparing these silicates and non-silicates. We've already named a few. Here's a chart that illustrates it. When this box moves out of the way, you'll see it. Over here on this side, silicates. 92% of the Earth's crust is made up of these. And they're broken down into 3 groups. Ferromagnesium silicates. Ferro means iron. Fe is iron. Ferro. It came from, I think, I'm pretty sure it came from the concept of fire because they refined the iron by using heat, fire. And so they thought somehow it was connected. It wasn't, but ever since then it's been iron is Fe. Magnesium, remember I said it's in the whole Earth more than it is in the Earth's crust. But it's unusual that it's down there because it's a fairly lightweight atom. Here are some of the ferromagnesium silicates. These are the ones that have high iron content with the silicates. And we'll hit these later. Biotite, hornblende, augite, and olivine. Now, just to give you a general feel for this, the ones at the top here, the biotite, it has high iron content, but not as high as the ones below it. So this is in increasing order of iron content. This is fairly light in iron content, which means it is a little lower density than the other, than hornblende, augite, and olivine. Olivine is a predominant mineral of the Earth's magma, which we'll get to later. Not magma, mantle, which we'll get to later. Then your non-ferromagnesium silicates, these would be those without iron in them, okay, but they're still silicates, okay. Quartz is a classic example of that. It's almost pure silicon oxygen, silicon dioxide, silicon oxides. Muscovite is also the name of white mica. These are the ones that have that high potassium content, that the potassium ion is stuck in between the aluminate on top and the silicate on the bottom, or vice versa. Okay, that's muscovite or white mica. Then your feldspars, these are aluminum silicates. Okay, sorry, I just dry out. Sorry, let me get a little carbonation on it and see if that'll help. I hate to do this in class, but I wouldn't be able to talk without it, I don't think. Okay. Feldspars are silicates with high content of aluminum silicates. Okay. Now that is as opposed to aluminates, okay, aluminum silicates. And in the feldspars, you have several classes of those. You have plagioclase, which is a sodium aluminum silicate, calcium feldspars, which are calcium aluminum silicates, and then you have orthoclase, which is a potassium feldspar, which is a potassium aluminum silicate. You don't need to know these distinctions, but you will run into these words, and you need to recognize they are silicates. All these are silicates. They just have different quantities of different other materials with them. And these other materials we'll see enter the picture of how these things form. So you'll run into these again. That's why we mention them now. Now, silicates are either got iron in them or they don't. Ferromagnesium or non-ferromagnesium. That's the big difference here. These are all minerals that are found in many of your rocks, okay? If you have a lot of dark color in your rock, the odds are you're ferromagnesium. If you have just a little pepper sprinkling of dark in there, you just have a little bit of these ferromagnesium. These are usually your lighter color, lighter density rocks, which will not have a lot of little black. So for instance, a beautiful piece of marble, okay, mostly non-ferromagnesium, the white part, but you have those little veins that go through it, that have that darker color. That's where the ferromagnesium part comes in. So you have the various crystals, minerals, more than one mineral in one piece rock. Okay. So where in the world do clay minerals fit in? What clay minerals are some of these other silicates. Once they've worn away, dissolved away, liquefied, whatever, and then reform as material, they're really, really, really tiny little crystals. Incredibly small crystals. Let me give you an example of how small. Okay? Remember the quartz. Oh, I don't have one with me. I thought I had my change in my pocket, but I don't. But picture a dime.
It's 4:15.
Oh, you're kidding me.
It's past 4:15.
It's past 4:15. How did you talk so long? Why were you doing that? Okay? All right. We are on this slide. Thanks for stopping me. On this slide, and we're just beginning to talk about the clay minerals. So that's going to be where we pause today. Sorry we didn't get as far as I thought we probably should have. We're still in the mineral part, and we haven't even gotten to the rocks. We'll get there. Okay, So that's where we'll leave off for now. I'll pick up the PowerPoint later. In fact, let me close that down now. Stop the sharing. Well, wait. I don't have to close it yet. What I do want to do, well, I am going to close it for now because I need to get somewhere else. Now, do I have everybody here? I think so. Okay. I'm going to minimize this for a moment, which is going to lose you for a moment. I think you can still hear me, but you can't see what I'm seeing, I don't think. I'm trying to end the slide, and I can't seem to get it to stop. So that's the one, I think. Okay. Now, what I need to do, I don't know if you can hear me. I need to undo this. There we go. All right. I'm getting there. Okay, Lab 4. Where's my Lab 4? I sent it to you, didn't I? No, Lab 3. We're doing Lab 3. Lab 3. I'm sorry.
I have a question. So tonight is going to be the night that we start looking at the moon this night.
Okay. We'll talk about that. That's exactly what our lab's about. Okay. So yeah, but it depends on when you want to start looking. Okay. Are you a late night person or early morning person?
I'm an early morning person.
I mean, really early, like before the sun comes up?
I used to wake up probably about 5:30.
Okay. It's probably getting a little toward light then, isn't it? Or is it? I usually get up.
Yeah, it'd be getting light by 5 from that.
Yeah. So I'm afraid that won't work. So you need to look for the moon at a time when the moon's visible. Now, the reason I say that, this morning when we got up to leave Georgia, it was right around, when we were packing the car, we got up right around 5. We were packing the car between probably 5:15 and 5:45. And then I saw the moon, and it was a little tiny little sliver, a crescent moon, and that was visible only in the early morning hours. And I mean early morning hours. So if you get up early enough, like before the sun comes up, you can start watching right now. If you're thinking more like, when I would say I would do it normally, would be, and I get up, usually I'm awake sometime around 5-ish or so, but I usually get up more like 6-ish. I may read a little or other things, but the time I would do, I put out my dog every night around 10 o'clock, to make sure she goes to the bathroom before we go to bed. Usually my wife's already in bed by then, but I usually stay up just to make sure she goes out one more time before the night. That's when I would look at it. Now, if you're that kind of person that are going to be up at 10 and it's dark by then, you're not going to see the moon tonight because the moon is a crescent. We're going to talk about this later. So that, it depends on whether you want to get up very early in the morning and look for the moon. If so, you'll see it. Or late at night, not super late, like 10 o'clock or later. It can be any time of night. Depending on when you're looking, you may or may not see the moon. You won't see the moon at 10 o'clock at night tonight because it's not going to be out there. It's going to be in the early morning hours. And we'll talk about that and why. So here is the lab. Oh, you can't see this, can you? Let me go back to Zoom. Trying to get by. There we go. And return to the meeting and share the slide again. Now, I'm sorry this is sideways. I did all these the same way, and I think they all came out sideways, and I don't know why. I need to move this out of the way. Okay, let me see if I can get it to move. You can't see this, but it's there in my way. Okay. So, here is the lab, and you've hopefully all got it, but if you don't have it, this is what it looks like. Now, I'm having to look sideways to read it. And you read this. I'm not going to go into all of this, okay? In fact, I see very little on this page I want to even emphasize. But read it. It's well worth your read, okay? And it's not going to advance that way. Oh, I guess I'm going to have to do it this way. Okay. Well, that's not working either. Why can I not get this to advance? Ah, there we go. Here is the time-consuming part of your lab. Okay? A complete cycle of the lunar phases, as we studied in the text, is just under 30 days, 29 and a half days. Okay? So what you're going to do, you pick a time that you think you can go out every night, either early morning night or late evening night. Pick a time that's convenient for you to do, and once you pick that, you will find out the moon is only going to be visible at that particular time for about 2 weeks. So those 2 weeks, that may be starting tonight if you're an early morning person. It may be starting in a week if you're a late night person. Something around there, okay? What you'll do, you'll follow the moon for at least half of a cycle with your observation spread over the course of about 2 weeks, because that's the only time it's going to be visible at that given time, whatever time you choose. And during that time, you'll be recording both the appearance of the moon and where the moon is. Okay, now when I say appearance of the moon, that is how much of that lunar disk you can see. Right now, like I said, it's a very thin slice, a very thin crescent, and only visible in the early morning hours. I looked at it this morning and said, they're not going to be able to see it tonight at 10 o'clock. It's only visible early morning hours, okay? Now, so that's part of what you're going to do. What portion of the moon is lit, okay? Over 2 week periods, it will go from a crescent and grow to a half moon, to bigger, until it gets a full moon, and start decreasing again. Or it will start, it'll go through some cycle like that. It depends on when you start. If you started in the early morning hours, you would have seen a crescent, a very thin crescent, at one time, and then it's getting thicker, and then at some point you won't be able to see it, okay? So, you're going to see, you will see it up to a full moon then. Okay, so you choose your time and it'll depend. So again, you're going to observe this not every day, okay? So the appearance of the moon is how much of the moon, lunar disk is lit, okay? You'll also be recording the position of the moon relative to two things. First is the landscape, okay? Now, I'm in a terrible position here to see the moon because I'm surrounded by trees. And what I do when I go out to look at the moon is I go out in the backyard when I put the dog out, and while she's off doing whatever she's doing, I'm looking around. And I'm surrounded by trees, which isn't a good thing, but I can still usually figure out where the moon is when it's visible. It's not visible now at 10 o'clock at night. But when it is, I'll be able to see it. And then I would say, if I face due north, which is just about where I'm facing right now, that's our walnut tree, okay? There, pecan tree's right in front of me, due north. Walnut trees are a little over here, another pecan here, the neighbor's house here, another across the road, the castle over there, it's a big old house. And then behind me is another neighbor, That would be how I would refer to things. Those would be, where is the moon relative to the landscape? The second feature is where is the moon relative to background stars. And this is why it can't be the very late morning hours, okay, like 5:30 or so when the sun's coming up. You're not going to see any stars because the sun is brightening up the sky. You're not going to see the stars. So you have to do it at a time before the sun starts dimming the stars. So that's the reason you have to do around the background stars. Now this morning when I saw it, I didn't notice very many stars around it because it was close enough to dawn that the sun, you could start seeing some things, so you couldn't see many stars. So that's why you need to pick at a time when it's fairly dark. Okay? So, what are some points in these observations? First, where are you going to make your observation? Like I said, I would go up in my backyard. Not a good choice, but that's where I look at it because that's where I am at 10 o'clock at night. Okay? Be better if you could find something like if there is a safe parking lot somewhere near you, like a mall or a big grocery store or Walmart or Sam's or Target or something that has a really big parking lot. It would be all right for you to go and safe for you to go there and go to the same place it's not every night, but every other night. You're going to do it over a 2-week period, but you're going to shoot for every other day. So you'd have no more than 7 observations usually. Quite possibly fewer than 7, maybe 5, maybe even as few as 4. Hopefully you can get, more than that. 5 to 7 would be great, okay? Might even be able to get that 8th one in, I don't know. But every other day, because only going to look for 2 weeks, okay? So that would be about 7 observations, if you can make them, and we're going to get to that. So choose your location somewhere you know you can be every other day for about a 2-week period. Now, if you happen to have sports field, that would be safe for you to go to, and go out to one position. They're not going to be playing baseball or something like that, or softball on it. Or a football field or something that no one would be practicing. If you could find something like that, that would be wonderful. If you don't have something like that, do the best you can. One of the students, now this was when we were on campus, this was several years ago, he was a work-study student for the night coordinator, the evening coordinator. So he got off every night right at 10 o'clock. So he'd walk out the back of the A building on the Bessemer campus, walk out into the parking lot. It was safe, nice place to be. He just got off work, walk out there and do his observation there. Every other night, he knew he could do it. Now, whether he came back to campus on weekends, I don't know. He should have, but maybe he skipped weekends. I don't know, and just picked up. So that's what you want to look for. If you can, be in the middle of an open field or parking lot, okay? But you need to be, it's important that you use precisely the same location for all your observations. So if it is that parking lot, okay, you need something to mark so you know where you are in that parking lot, okay? Or if it's an open field, you need something. What you might do is get a piece of yellow tape or something like that and just put a nail through it and put it into the ground there and hope that the mowers don't mow it up or something like that. Or find some way that you can get to that place, that same spot every night, okay, or every other night. So there's your location. Find the best place you can near where you live. Now, you don't want any bright sources of light. So if it's a parking lot, it shouldn't be a lighted parking lot. And that's why I said make sure it's safe, okay? So it can have enough lights to be safe, but you don't want it blaring lights. You'll never see the stars then. May even be hard to see the moon then. So you've got to, it's a give and take here, okay? Backyard may work for you, that may be, but you want just as little ambient light as possible, Okay. Now, the first time you go out a little early. Okay, or ahead of your time, and we'll talk about that in a minute. And that night, you figure out, like I'm sitting here, if was going to do my observation directly from where I am, but out in the yard, with that pecan tree right due north of me, then I would put the pecan tree there, the building here, the neighbor here, the red oak down there, something that I can identify things all around me. So you need to be able to do that. That's why you need to be in the same location every night so you'll know exactly where you are. Now, timing your observation. And I've given you about all I can. It depends on you and when you're free and available to do this. But what you need to do, it's critical that you make all your observations at the same time of night within 15 minutes. So if you're, say, 10 o'clock at night, you could be as early as 9:45 or as late as 10:15, but don't be any outside that range, okay? So you need to have something like, I put out the dog just about every night, right around or after 10:15. So I would right after 10 o'clock. So I would shoot for 10 o'clock or maybe 10:05. That gives me time to orient myself. That first night I go out there at 9:30 or so, just to get all the orientation done that I needed to do. And then after that, be there a few minutes ahead and go for it. Okay. Now, because weather may hamper your observations, that is quite a statement. Because what do we mean by weather? Well, certainly if it's raining, don't go out there. Okay, you're not going to see the moon, maybe. But you certainly won't see the stars. You may have trouble seeing your landmarks. Okay, so that's not a good. Don't get out there in the rain. But even if it's a cloudy night, you may have difficulty either seeing the moon or the other stars and stuff. So when you have one of those nights, try to pick the next clear night. So if you did every other day, like you did day 1, and you skipped 2 and went to 3, and you skipped 3 and went to 5, but 5 was a cloudy night or a rainy night, then go on 6. Don't wait until 7. Go the next night. If it's clear, then see it not. Okay. So do your best to do every other night, unless weather wipes you out. Then go get off your odd numbers to even. Get the next best night that you can. Okay, and then pick up every other night from there on. So if you did 1, 3, 6, then do 8 and 10. That kind of thing. Every other night that you can, unless of course weather kept you from it, which I guarantee you we're going to have some cloudy nights and maybe even rainy nights. Okay, so what do you record? In order to record the position of the moon, the appearance and position of the moon, you'll need to make now they say a sketch. A sketch, notes, whatever it takes for you to know. If it were me, I know my backyard, so I would pick that pecan tree. The walnut tree is pretty close, but maybe my shed, tool shed there, maybe the neighbor's pine tree over here, possibly, I'd pick something sort of outlining all around me. Now, if you're out in the parking lot, maybe the Sam's store here, the Walmart here, the light pole there, the flag pole there, the traffic light here, whatever you're choosing. If you're out in the middle of a sports field, whatever you can do. The concession stand for this field here. I see a signpost on the highway over here. I see a big old tree here. Pick you something along your horizon you can always refer to. And when you get in your spot, you orient yourself just right. Okay? And in my mind, that would be going due north. But that's just how I am. Anything else, you can pick it from anything that's convenient for you. Okay? Now, what do you observe? Like I said before, they say make a scale drawing, that kind of stuff. However you want to do that, you can do it. Okay? But what you want to do is to complete your first observation and give yourself enough time, like I said, about, I think, 15 minutes ahead, possibly 30 of that first night, so you get everything down. Then after that, you know exactly what you look for, when to look for it. Okay, so that's what you're going to observe. Okay, now it gives you some guidelines, and these I find not all that useful, but if you want to use it, you can. Okay, I'm going to try to give it to you. When you hold your hand out as far as you can from you, the width of your outstretched hand, now your arm is straight directly in front, width of your outstretched hand from thumb to little finger, that is 22 degrees. I would not do it this way, but you could. Okay, if you hold your fist out there, straight out ahead of you, from one side to another side, that would be about 8 degrees. The width of your 3 middle fingers, that would be about 5 degrees. Okay, the width of your index finger, okay, that would be about 2 degrees. Now, I wouldn't use that, but if you wanted to, you certainly can. Here's what I think would make more sense, okay? And they give you some scales. Alternatively, carry a ruler with you. I would say a yardstick, okay? Now, you might want to carry a little pin light or something like this so you can see on the yardstick. Because what you want to do is hold that yardstick at arm's length, straight out, arm's length, from your landscape, your key point on your landscape. That promontory, the base of that promontory to the ground, how far up is the moon on that yardstick? And then when I go over here to the oak tree in the neighbor's yard, how far up from the moon is that? On that yardstick, okay? When I go over here to the power pole here, whatever it is I'm using, the traffic sign, the billboard, whatever I'm using as my landscape reference point, how far up, right, left, turn that yardstick each way, how far up and to the right that is. So many inches up, so many inches to the right. You don't need to know degrees, just something that you can measure and write down. You write down how far up and to the left the moon is that night, how far up and to the right it is the next night. Okay, I did it backwards, but whatever. That is the thing that you want. To me, the ruler would make more sense. Now, if you aren't good with directions and you don't know where true north is, somebody in this class, I'm trying to remember who it was, said when I said I was going to the farm, they said, you're probably going to get some really good stargazing, aren't you? Was that Kermisha? I don't remember if it was you or it was one of the women in the class said that. I didn't catch which one it was. I don't remember. One said that. And sure enough, I did. I could see, and now one night was cloudy, but the 2 of the nights when I put the dog out, there was a Big Dipper just as clear as day. I mean, just perfect Big Dipper. I looked at those 2-point stars and found the North Star. Never could see, I thought I saw a little bit of the Little Dipper, but I never can see all the stars in the Little Dipper. But I knew that North Star. So head to the north. Okay, that is how I would do the north. Or you can get your little cheap compass from a store somewhere. If we were back on campus, I'd give you a compass because we have probably 4 or 5 there. If you needed one, I could give you one, okay? But we're not on campus. So do that. If you're in your car and your car has a compass in it, you could use that. Ours is not very good. North would be anywhere from there to there, So, but if you have a good idea, but make sure you use the same position, even if you're not right on the money with what true north is. If that's what you think it is, go with that and keep that. Okay? So one thing is relative to your landmarks, things on the earth, the traffic sign, the billboard, the power pole, the light pole, tree, the big tree, the sap, whatever you're using as your reference points, then make your measure from the moon of the one that's closest to and how high, and you know how they're distributed among each other. So you can figure out where the moon is night after night, night after every other night. Okay. Now, read this. It has more information in it. Here is the key. One question, your first question on this lab, and this you won't be able to answer until you're through with your 5 to 7 observations over a 2-week period. How would you describe the night-to-night path of the moon with respect to the landmarks around your observing site? So let's say, I'm just going to make this up, don't think this is anywhere near. Let's say the first night I saw it, when I was standing, like this morning when I was looking at it, if I were standing in our front yard at the farmhouse, due north, the moon would have been almost 90 degrees to the right, and it would have been above the intersection of the crossroads there, and I would have measured how far it was directly above that, or maybe 3 inches to the right of that intersection. Okay, I could see the intersection from our front yard. Okay, that's what I would have measured. Then the next night, maybe it went from left to right. When I was facing due north, it was going left to right, or right to left, going higher in the sky, going lower in the sky. Whatever. You give a description of the night-to-night path of the moon with respect to the landmarks, the things that you see on the earth, okay? And if you got a fairly good description of where you are and what you're seeing, you'll know where the moon's going. So that's the first question you need to be able to answer after the 2 weeks you started seeing the moon. Where is it going night to night? The second question, in which direction does the moon move with respect to the background stars? So here's the second thing you're looking at. When you see that moon, wherever it is, this morning it was over here, not too high above the horizon there. Unfortunately, I couldn't see the background stars, but pick a group of stars near where the moon is that have a certain pattern. It doesn't have to be a constellation. It doesn't have to be anything. Some pattern you can recognize. And draw those stars. That first night you see it, draw those stars around the moon. It formed a little triangle, or it looked like a horse's head, or whatever you choose that you can pick out that. And pick out some other stars near that, okay? And then the 2 nights later, it had moved over here. Well, it moved so many inches, if you're using a ruler, to the left, and went further up. How many inches? From that first set of stars. So your second observation, in which direction, and that would be better to do north, south, east, or west. That would be ideal. But if you aren't good with directions, right or left would be all right. How far, in what direction did the moon move with respect to the background stars, night to night? It's not consecutive nights, but and if you leave every other day, you'll notice at the same time, you'll notice a definite shift. Okay, so how would you describe the night-to-night path with respect to your landmarks, whatever you choose as your landmarks, and from the stars, surrounding stars, the background stars that you've identified that you know you can pick out night after night? And then the third question you answer is this one. It's actually you draw the graph. And last night, or this morning, I would have said that star, if this would have been my first day, would have been between 0 and 1/4, because it was a fairly thin sliver. So I would have made a little mark right about there. Can you see my cursor? I would have made it there. And then the next night, it's either going to be this is 2 nights later, so you skip a day here, go to the next day. It's either going to be bigger or it's going to be smaller. Okay? One or the other. It's not going to be the same. And then 2 nights later, or whenever I see it next, it's either going to be bigger or smaller, okay? And at some point, you might see it get bigger for a while and then get smaller. You might see it start fairly good size, get smaller for a while, and then get bigger. You're going to see a change night after night. Now, these are the days. You won't ever have 2 days consecutive. It might be day 0, 2, 5, 7, 9, 11. That may be your observations that you'll see. Maybe more spaced out than that, whatever. Those are the ones, but draw the moon. If it's a quarter of a moon, a half moon, 3/4 of a moon, or full moon. Okay? But you put in there where you are on that day, and you draw a little moon there.
So, Dr. Fowler, for number 2, that's where you want us to draw the moon we see each night, then graph it on the chart.
Okay? Now, how you do it, I don't care. If you want to draw it on a chart, certainly good. If you have a chart and you put those background stars, the ones that look like a triangle or a little square or a horse's head or whatever you want to choose, and then describe the moon. Is it getting further from that? Is it moving to the left, to the right, north, south, up, down, whatever? You describe it relative to the background stars you can pick out. It doesn't have to be real close to them to begin with, but relatively close, so that then if it passes them, you can watch it pass them. Or if it gets further from them, then draw the next group of stars and how they are relative to your first group. So that's relative to the stars. What I'm looking for is the answer to this question. Describe the night-to-night path of the moon with respect to the landmarks around your observing site and with respect to the background stars. And this will be going east to west, north to south, west to east, right to left, up and down. Somehow describe the path relative to your observations, your landmarks, and relative to the stars. And they may not be the same because the stars are moving a little bit too. Not much, but a little bit. So that's what I'm looking for those two. For the third question, you're just filling in the graph here, where the moon is. Just put your little dot where it is that first night, the next night, the next night, the next night, the next night. And it won't be every night, every other night, So put it over the day. You're not going to get 20 nights worth, I guarantee you, because the moon's not going to be visible for 20 nights. The maximum it would be about 14 or 15, okay? So, and I doubt if you'll even get that. So, do what you can, okay? So that's what you're going to do. You may not be able to start tonight because the moon may not even be visible tonight, but you can go out there tonight and figure out where you're going to stand and which, and get your landmarks and that kind of stuff. Now, if it's raining tonight, don't do it. Okay. Go the first clear night, figure out where you're going to stand, figure out that spot, figure out the time you're going to do it, and then if you want to do drawings or description, write it down on a pad, anything like that. And then go out every night until you see the moon the first night. First night you see the moon, that's your day 0. And that's when you start recording. Okay? Then skip a night and the night after that. Skip a night and do the next night. If it's raining or cloudy, then go the next night. Okay? Don't skip a night if you didn't make an observation the night before. Go the very next night. Okay? Does that make sense? Does that answer your question? I wasn't sure if I got it.
Yes, sir.
Okay, good. Now, that's 3 questions of the lab, and it's going to take you weeks to do that, those 3 questions. Okay. Here's the rest of your lab. We're going to do this tonight, this afternoon. Okay? I'm sorry this was printed sideways, but if you got it up to right, you can do it. Okay. Now, they mentioned several things here. When the moon is exactly or almost exactly between the earth and the sun's over here, the moon's here, and we're here. My head's the earth, okay? The sun's way over here and the moon's here. And if we're lined up like this, okay, the sun is lighting that side of the moon, not lighting this side. This side's dark, okay? So therefore I see nothing lit. I might barely see the shape of the moon, But guess what? It's going to be in the daytime, because the sun wouldn't be up there if it wasn't. So that would be a new moon, okay? It's between me and the sun. So, and it usually is going to be around in the sky almost all day long, okay? Not days like we have now, which are 15 hours long, daylight, but it'll be there a lot of the time. That's what we call a new moon. Okay, now, again, the sun's here, the moon's here. Now, everything's moving, but let's just imagine the moon moves here, okay? Now, the sun's here, the moon's there, and I'm looking at, well, let me do it this way. The sun's here, the moon's over here. I'll look at the moon, and only this half of the moon's lit, because that's a half toward the sun. That would be called a half moon. Now, anything between the new moon and the half moon is just going to be a little bitty sliver, and then a bigger sliver, until here it's half a moon, okay? Now, keep on going around, and over here it's more than half a moon, because the sun's back here, most of the moon's being lit, and more and more and more until all the moon is lit. That would be called the full moon. And then after that, it's going to be partial moon, still most of it, but still just a partial. So now it's less and less and less until it gets here, and now it's exactly half a moon, because the sun's over here, remember? Only I see half the moon, okay? And then it's less and less and less. Now I'm seeing a sliver. Those slivers are called crescents. The bigger than half, but not full yet, is called gibbous. And those are all terms we see here. Okay? So the first half moon after a new moon is called the first quarter moon, because it's a quarter of the way around. Okay? So it's called the first quarter moon or a half moon. Either one. I don't care what you call it. When more than half the moon, when less than half a moon, so it's when it's between a new moon and the first quarter or the half moon, that's called a crescent moon. It's just a sliver. Big sliver or small sliver, but it's less than half a moon. That's called a crescent moon until it gets to be half or first quarter moon, then that's what we call it. Once it's bigger than that, over here or anywhere there, that's called a gibbous moon. More than half. Until it gets completely full, and then we call it a full moon. Okay? Now, once it passes full moon, it's still gibbous, because it's more than half, until it gets here, and then it's a half moon again, and then it becomes a crescent again. A big crescent, little, smaller, until it's a new moon again. So those are the things. When the moon's growing in size, like going from a new moon to a half moon, that crescent phase, it's waxing, getting bigger. And then when it's a gibbous over here, getting bigger, it's waxing again, but it's a gibbous waxing. When it's a full moon, it's a full moon. That's all it is. Then when it starts getting smaller, still a gibbous moon, more than half, but getting smaller from a full moon, that's a gibbous waning, because it's getting less every night. Until it gets a half moon again, or a third quarter moon, and then that's all it is. But it's waning because it was bigger and now it's going to be smaller. So it's still waning, and crescent waning, until it's just a tiny sliver of a crescent. Then it's a new moon again. Okay, does that make sense? All right.
Of course not.
What's
Of
that?
course not. Of course not.
What is confusing about it?
Go over the waning and the waxing one more time.
Okay. Waning means it's getting smaller. Okay? So say it's a full moon. First time you see it. Well, when we're doing our lab here. And once it's past full moon, it's now a gibbous moon. It's bigger than half, but not full. It's gibbous, but it's getting smaller night after night. Waning. Until it gets to be a half moon. That's a gibbous waning. When it gets to be a half moon, it's a half moon waning, because night before last it was gibbous waning. Next night it's going to be a crescent waning, so this is a half moon waning. And then from this it's getting to be a crescent every night. A big crescent to begin with, but then smaller, it's waning, it's getting smaller, until it's a new moon, and then you don't see it at all. That's just a new moon. But then after a new moon, it's getting a little bigger. It's a little bitty crescent now, like this, okay? Little bitty crescent. Then the next night, it's a slightly bigger crescent. And then the next is bigger. That's a waxing crescent. Crescent waxing until it gets to be a half moon. And then it's a half moon waxing because it was a crescent not last night. It'll be a gibbous tomorrow night. So it's growing. It's a waxing moon. Half moon waxing. And now it's a gibbous moon, but every night it's getting a little bigger, so it's a gibbous waxing until it's full moon, and then it starts gibbous waning again. Does that help? Yeah.
Okay, so waxing means it's getting larger.
Larger, more is lit every night.
Okay.
And waning means less is lit every night. Night to night is getting a little bit less every night. And that's why I want you to do it every other night, or the lab wants you to do it every other night, because you might not be able to tell one night after another, but after 2 nights, you'll say, oh yeah, that's smaller than it was 2 nights ago, or it's bigger than it was 2 nights ago. So yeah, that's what it means. Getting bigger is a waxing, getting smaller is a waning. Okay, if it's between a new moon and a first quarter or half moon, that's a crescent. If it's between a half moon and a full moon, that's a gibbous. Full moon and a half moon, that's a gibbous. Half moon and new moon, that's a crescent. So the crescent means it's a little sliver. The gibbous means it's more than half. Okay. And then whether it's growing or shrinking, that's waxing or waning. So here's what we're going to do. All right. Now this page is a little oddly put together. And it's because some of these are figures and some of them are fill in the blanks. Okay? We're going to start with the middle of the page right here. So I hope you've either got it on hand, or if not, and you want to just draw it, you can. But draw something that looks like this. Now, in the book, the sunlight was coming from this side. In our lab, it's coming from this side. Here is the Earth in the middle. And of course, the half of the Earth that's toward the sun is lit, the other half is dark. Now, the white is lit, so you color, well, it's already colored in for you. So the first thing you've got to do tonight, do it right now if you've got it in front of you. If not, draw you an Earth in the middle, bigger than the moons, and then 8 moons around it just like this. And show that the sunlight's coming like this. So if you don't have your lab in front of you, this page of your lab, draw it on a piece of notebook paper. Take your time and do it as neatly as possible. And once you've got it, if you've got this lab in front of you now, draw you, just like you see here, a vertical line that's perpendicular to the sunlight. You know, a vertical line like this. And draw in every moon. Every moon. A vertical line in number 1, a vertical line right through number 2, right through number 3, right through number 4, a vertical line through each of those moons. Okay? Pretty easy to do. Just draw that vertical line just like you see B to D here. Draw it just like that in each moon. All 8 moons. And
Dr. Fowler.
Yes.
This is the only lab we doing today, right?
Yes.
Okay.
Are we running out of time? Okay. We go
I
to
already did this.
What's that?
I already got this lab done.
Okay. What I'm doing right now. Okay.
Yeah.
I hope that you always colored in the back side. Just like this Earth is here, it's only the back side here. Like number 5 is from the middle of that vertical line to the 5. Here it's from the vertical line to just above the 6. Here it's vertical line to the left of the 7. All this is, every one of these moons you draw in exactly like this Earth is, with the back side, the side to the right of that vertical line dark, and the left of the vertical line dark, to the right of the vertical line is, you don't draw a thing. It's light.
So you saying, so basically we making the moons just how the sun is set up?
No, just how the Earth is set up. Just like this.
Yeah.
A vertical line right through the center of all 8 moons, And
shading the left side in.
The left side is staying the left side in and leave the right side bright. Exactly.
Okay.
Okay. So I hope all of you are either doing it or have already done that, right? And if you want to, if you have your book and you want to refer to something in the book, just remember the book is exactly opposite of the sunlight. On page 426 or your page 16-20 is figure 1629. It's in section 16.5. You'll see 4 moons around one Earth, and you'll see how all 4 of those moons are just like the Earth, a vertical line, but on that one the sunlight's to the left and the darkness is to the right. On ours, the sunlight's to the right and the darkness is to the left. You color in the dark side, the dark side. Leave the lighted side white. Okay. Now, at this point, we're going to imagine ourselves on the Earth. That's where we are, right? And we're looking at the moon. And you've colored it in, right? Okay? Look at moon number 1. And you're on the Earth looking at moon number 1. What do you see? You're on the Earth down here looking at this moon here. What do you see? Only the dark side, right? You don't see any light at all because all of the light is on the other side from you, right? Yes or no?
Yes.
Okay. So therefore, down here on the bottom, you color the whole number 1 dark because you don't see any light from the sun. The moon's between you and the sun. So the sun is lighting this side, the right side of the moon. You're only seeing the left side. It's completely dark, right? So number 1 down here, you darken the entire circle. Yay?
Yes, sir.
Now, when the moon is moved over here, okay, remember the vertical line is here. The left side is dark, the right side is light. You're here on the Earth looking at that. You see just a little sliver of that white side. So number 2 here, from the upper portion here, just draw a little bitty sliver that's light, okay? A little sliver that's light, and color in all the left of that little sliver. So just leave a little sliver of white here. No white here, a little sliver of white on the right side. The lighted side is always on the right, the darker side is always on the left. Here, most of it's dark, but there's a little sliver of light on the right. Do you see that? Now you look up here at this moon, and what do you see? You see exactly half a moon. Just what you see for number 3. The right side is white, the left side is dark. Okay? So number 3 looks just like number 3 here. A vertical line through this with the darken in the left side. Just like you did for number 3 here. Okay? Number 4, you're over here, you look up to see the moon, and what do you see? You see mostly the light side. You don't see the whole moonlight, but most of it is. Okay? So what you do here for number 4 is draw you a little sliver to the left side, just a little sliver from top to bottom to the left, and darken in just that little sliver to the left. Leave the whole white right side and most of the left side white, just that little sliver over here is darkened. That's number 4. Do you see that? Now when you're on the surface of the Earth and you're looking at this moon, you're here on the Earth, you're looking at this moon, what do you see? Number 5 here. You look up at it, and everything you see on that moon is totally lit. So number 5 is don't darken in a thing. That is a totally white moon. Totally lit. leave that 5 alone. Don't put a single mark on that 5. Okay? Number 6, look at this moon when you're here on Earth, and you see the moon has that vertical line in it, but you're looking at it and you see mostly the light side and very little of the dark side. So for number 6 here, it's just like number 4. You draw your little sliver to the left and darken that little sliver to the left, leave the whole right-hand side and more white. The only part you darken is the part to the left. Just a little sliver to the left. Look at number 7. And what do you see? You're here on Earth looking at 7. What do you see? Anybody?
It's going to be like number 3?
Exactly like number 3. You see a perfect half moon. And so number 7 down here, draw your vertical line from top to bottom, just like you did number 3, and color in, darken in the left-hand side, leave the right side white. That's a half moon. Okay. And then number 8, you're looking at number 8. Remember, your vertical line is here. The half mostly toward you is dark. What do you see? Just a tiny sliver that is white. So make you a tiny sliver on the right-hand side of the moon, just a little bitty sliver. That's the only part you leave white. You darken all the rest of the left-hand side and more dark. Right? Does that make sense?
You said darken
Yeah.
the left side?
Darken the left side a little. No, the right side.
Okay. Now, always what you darken is you only darken the left side. Look at the Earth there. Only
And
the
the
left
line
side
goes
of the
right
Earth is
side.
darkened.
Right. Okay.
Now, the question is, up on these that are around the Earth, these 8 up here, every one of them looks just like the Earth. Vertical line down the middle, left side dark, right side don't do a thing.
Not bad, yeah.
These down here, you're going to vary the amount of light and dark. Number 1 is totally dark, color it all in.
Right, okay.
Number 2, just a little sliver to the right is light, and everything else is dark. Number 3, the half to the right is light, don't touch it. The half to the left, the whole half, just like number 3 up here. In fact, every one of them up here, they look like a half moon. The right side is white, don't put a thing there. The left side is dark, color it in. Number 4, do a little sliver on the left-hand side, and that's the only part left of that is what you darken. Almost all of it is white. Number 5, it's all white. Don't put a single pencil mark on that moon, that circle there. It's a full moon. Number 6, just like number 4, do your little sliver to the left and darken that to the left. Leave the whole rest of it white. That's more than half of it. It's going to be left white. Just a little sliver over here, darken. And number 7, again, just like number 3, it looks just like 7 here. Vertical line down the middle and the darkened part to the left. Don't touch anything to the right. Then number 8 is just like number 2. You're looking from the Earth. You see mostly dark with just a little sliver. That's what I saw this morning, was a little sliver toward the sun. Always the white part is toward the sun. So do your little sliver on the right-hand side. Don't color that in, but color everything to the left of that little sliver. Darken it. Okay? So you've got the middle part done and the bottom part done, right? Yeah. Please use pencil so you can erase. I hope you haven't gone too far with ink. Now, what we do at the top is fill in the names of these moons at the bottom. And it's just not the name. It says in the spaces below, write down the names of the phases corresponding to the sketches and down here at the bottom. include whether the phase is waxing or waning. So you look at number 1 down here. What would you call number 1? When you look at it and it's all completely dark, what do you call that moon? It's not an old moon, but it's a
new moon.
A new moon, you got it. Okay. Now, a new moon is neither waxing or waning. It's just there. It's a new moon. Nothing is lit. Okay, so don't worry about it. But number 2, when only that little slice toward the sun is light and the rest of it's all dark, what do you call that one? I'll go back 1 page. Here it is. The crescent moon. Crescent. The crescent moon. Now, is it waxing or waning?
Waxing.
It's waxing because a few nights before it was totally dark. Now just a little bit is light, so it's waxing. Perfect. Okay? Then you look at number 3 here. And it's exactly half and half, so what would you call that? Go back to the previous page. And it's either called
Half moon.
a half moon would be fine, or a first quarter moon. Either one of those would be fine. Half moon takes less room to write, so I would probably go with that. But is it waxing or waning?
Is it waning?
No, wait. It was just a little sliver the time before, and next time it's going to be bigger, right? More is lit, so that's it's still waxing. So that'd be a half moon waxing. Number 3. Number 4, what was that? Had just a little sliver on the back side that was dark, and all the rest of it was light. So more than half of it was light. What do we call that one? All right. When more than half of the moon's disk is visible, we have a gibbous moon. Gibbous. A gibbous moon. Okay? And the next part of that question, is it waxing or waning? This is number 4. Down here, is it waxing or waning?
Still waxing.
It's still waxing because it was just a half moon on 3, a gibbous moon on 4, and on 5 it's going to be even more, so it's gaining every night or every cycle, okay? So number 4 was a gibbous waxing. Number 5, what would you say that was?
Full moon.
Full moon, you got it. And you don't have to put waxing or waning on that one, because how can it be? A full moon is a full moon is a full moon. It's not growing and it's not shrinking yet. Okay, so a full moon, all you have to put. Number 6.
Gibbous waning.
Gibbous waning, excellent. Way to go. Okay. Number 7. How would you describe that one?
Moon waning.
Say that again.
Half moon waning.
Absolutely, a half moon waning, because half of it's lit, half of it's dark. Half moon. You could call it a third quarter moon if you wanted to, if you're a football fan. No, I'm just kidding. But it's definitely waning because it's getting less lit every night. Okay, and then number 8.
Crescent waning.
Crescent waning, you got it. Nailed it right there. Any questions on page 383? Harry, I see you lit up, but I don't hear anything.
No, we're good. We're good.
Okay, good. All right. Any questions before we leave 383? Okay. Let's move to sadly, the last page. Okay. Here it is. It should be 384, but I must have cut that off the bottom. At what time of day would you expect the full moon to rise? Now here is where, again, we picture the sun over here, and if it's a full moon, that means the moon's over here. Now, you can give it to... Say again?
6 o'clock?
6, okay, you mean AM or PM?
Oh, PM.
PM, you're absolutely right. Because right around 6 o'clock, when the sun's going down, the moon would be rising. Because they're right opposite each other. Okay? So that would be 6 o'clock. PM. Be sure you put the PM. Now, number B. The new moon, or a very thin crescent moon, if you can't see a new moon, when would it rise? Well, the new moon is going to be on the same side as the sun. Okay? So what time would you expect it to rise? It's right with the sun. So when would it rise?
12.
Second? I couldn't hear you. I heard you say something, but I couldn't make it out.
I think I got it wrong. I read it wrong. I was writing the answer and I put it wrong.
Okay. Anyone want to make a guess? It's right there with the sun.
Okay, I can't hear you, but it sounds like you're saying that it's going to come up with the sun, right?
You got it. And what time would that be approximately?
5:45?
Well, okay, yeah, but let's say 6 a.m. Because right now we're in summertime. The sun may come up a little before a new moon because, you know, remember, it's only going to be visible about 12 hours. So let's say around 6 a.m. It may be plus or minus. We're on daylight saving time. It's hard to say. But let's say around 6 a.m. Or you could just put around sunrise. That would be fine too. We don't have to put an exact time. Okay?
Dr. Fowler, we can't really hear you.
Okay, well, I'm trying to face the... Is this better?
Mm-hmm.
Okay, I'm sorry. I'm trying to face it, but when I'm also trying to get it so you can see my hands. But if I do that, I have to move back from the camera. So it's hard to get, again, the camera and the microphone. This new computer they gave me, the microphone is way too directional. Okay, I'm sorry about that. My old computer, as far as I know, I could talk anywhere around it and it picked it up. Okay, so, but it's
okay,
dead.
so with 5A, with the full moon time, which was 6 p.m., you said that came up the opposite time as the sun, right?
Yeah, because it's opposite the earth as the sun. The sun's over here, the moon's over here. So when the sun would be rising, it would be setting. When the sun would be setting, it would be rising because it's opposite. So that would be right around 6 p.m. Because you see the full moon all night long because the sun's going to sleep, the full moon's coming away. Okay? That's a silly way to say it, but does that make any sense? Okay. Now let's do the first quarter moon. The one that the moon is back here, the sun's over here. What time would you expect that to come up? Let me put it this way. I saw a very thin crescent moon about 5 this morning. Okay? No, it was later than that. And I was also on Eastern time, so it was in daylight savings. So it was right before sunrise. Okay? The new moon would be at sunrise. This was right before sunrise. So the first quarter moon would be a little bit later than that. I'm sorry.
Would it be 5 a.m.?
No. That wouldn't be first quarter. Okay? It would be 90 degrees off or quarter of the night. So that would be about halfway through the night. Okay, the new moon came up with the sun, and then the crescent following the new moon would come up as that was growing. That would come up a little later in the thing. So that would be the half moon or first quarter moon over here would be okay, let's think of this a moment here. New moon's here. First quarter would be over here. So the new moon is getting a little bigger, a little bit later every morning. Okay, so it'd be later. So I'd say the first quarter moon would probably rise right around noon. Wouldn't you? Wait, am I going backwards? No, I think it'd be going toward midnight. I think it would be midnight and that first quarter would rise because it'd be a little bit later on the rising. Okay?
So it'll be 12 a.m. instead of
Well,
p.m.
I'd say 12 noon because I don't know which a.m. and p.m. you talk about. Just say 12 noon.
Okay.
Okay? Now, the third quarter moon to rise, what would that be? If this one rose at 12 a.m., at 12 noon, this would rise at
midnight.
At midnight. Okay. All right. There was a song that way, wasn't there? Never mind. Okay. How about the first quarter moon to set when it goes down? If it rose at 12 noon, what time would it set? It's only up about 12 hours.
It's not midnight? I thought
That would be midnight too. The third quarter moon would rise at midnight, but the first quarter moon would set at midnight. Okay, so those two are the same. How about the new moon?
Wait, yeah, going backwards. Yeah.
Say again?
No, I was saying just like the other chart, it's going backwards. So
right.
Where B would be E and then A would be F. Right?
Yeah, okay, right. Okay.
Yeah, so like F is 6 p.m.
Exactly. You got it. So that would be the new moon would set right when sunset, right around 6 p.m. Yeah, right. You're absolutely right there. Okay? Now, I want to point something out to you. Okay? You have answered already, or we've talked about answering. There's 6 questions there. There's 8, 16, 24 there, but 6 of those 24 have 2 parts, so that would be up to 30. You've answered, or we've talked about 30 out of your 33 points possible answers for this lab. So get the other 3, okay? That is really where you're going to learn a lot. But don't just, if you don't get the other 3, if you don't do it, don't say, oh, this will be the lab I drop. Because we just talked about 30 out of 33 of the answers. So please turn this in 2 weeks, in 2.5 weeks, whatever it takes you to get your observations. Even if you get the observations wrong, you should get all this part right, shouldn't you? So, yeah, don't. I've had so many people say, oh, no, I'm going to drop that one. I didn't get to observe the moon. Hey, if you paid attention in the lab, which I think y'all have been doing, you should have 33, or awfully close, the 30 of the 33 questions, possible points correct. However, it's 25 possible points, but 30 out of 33 pieces of that, you should have awfully close to being correct. So please don't fail to turn this in. But see if you can get the other 3 pieces so you get your perfect 25 points. Otherwise, it's going to be some fraction of that. Okay? Any questions on that? Yay or nay?
No, sir.
Okay.
I actually do. No, I don't. I'm sorry. No, I don't. We're good.
Okay. Now, if you need more time to draw your pictures and fill in and that kind of stuff, I'm willing to stay at least until 6:15. But if you've gotten everything you can, I hate to do it, but I may cheat you out of part of your tuition dollar here.
Do you have to take roll again, Dr. Fowler?
Oh my goodness, why didn't you say something earlier? I was supposed to do that at 4:45. Thank you. Okay, Don didn't make it in at all today, did he? I haven't seen him. Capri, are you still here? Let me see if I can pull up my thing. Where is my cursor when I need it? There we go. Let's see, participants. Okay, I've got Harry here. He's been asking questions, so I know he's been here. Okay, I've got Capri, she's still here. Okay. Is Bridget still here? I don't see her yet, but I haven't gone all the way through. Cormisha's still here. She's been asking questions, so I know she's been here for lab. David is still here. Had trouble getting in, but glad you made it. Jacob's still here. All right, good deal. Let's go on down the list here. Juan is still here. Good deal there, if I can find you. I know you're in here, so there you are. Okay, Juan's still here. All right.
Yes, sir.
Say again?
Yes, I'm still here.
Yeah, I got you. Okay. Now, let me go on down the list here. Nikia's still here. There you are. And Roy's still here. He's been communicating. And let's see who else. Thomas is still here. Good deal. Okay, who else? Valerie, is she still here? No, I guess so. Okay.
I am.
I know, I've been hearing you. Okay. Now let's see who else. Okay. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this says we got 11 on the 11th. Yep, I think I got them all. Thank you for reminding me of that. So that means that we've lost Bridget. She's not here, but she was here earlier. Scott never made it in today. We haven't seen Mason from Haley Mason from the beginning. Patrick didn't make it in today. Parisha, I guess, no, Caitlin we lost, didn't we? Yeah. She's not here now, I don't think. Has she been here at all during lab? Have y'all seen her? Okay, Parisha, I don't think made it in at all today. Harry we got. Cormisha we got. Rod didn't make it in at all today. Jacob we got. Haven't seen Antonio Tremaine Weston from the beginning. David we got. Leon didn't make it in today. Okay. So now I've got the roll called up. Thanks for reminding me. Any other questions, issues, concerns? You want me to stay on the line while you finish your lab and I'll answer any questions you may have? Or are y'all wanting to eat supper now and finish it later? Or whatever. Let me know.
I think I'm good.
Okay. Is that everybody's consensus?
I think we're good.
All right. All right. Well, that'll give me a little more time maybe to start copying or printing some of your tests and other things off. So I'll try to get to doing that while y'all are working at this. So that means I'm going to turn off the Zoom. So speak now or hold your peace at least until next Wednesday. All right, to stop. Okay, I'll stop the sharing first. And then, unless there's somebody else have something to say, I already see people leaving, so that's fine. I'll end the end the meeting, and then I'll end the recording. So take care. We'll see you on Wednesday.